At this moment, I will explain about the material of graph theory and how it works.
In this video, I'll give you a brief intro into the vast and incredibly interesting field of graph theory from a computer science perspective. Here's an example of a type of graph that we're going to talk about extensively in this video. If you were to ask me what's the simplest definition of a graph for someone who knows nothing about the field, what I could tell you is that you can think of a graph as a network that helps define and visualize relationships between various components. In this example, the circles that you see represent the components, and the lines connecting them can be thought of as signifying a relationship between the components. These ideas, of course, have more formal name than graph theory. We refer to these circles as vertices or nodes, and the relationship signified by connecting lines represent what we call edges in a graph. Graph theory is all about the study of the properties of these types of networks, and how they can be used to model and solve a whole host of interesting problems. This video is all about introducing you to core concepts related to graph theory that we will then use to study fundamental graph algorithms. We'll first start with an important discussion on why we should even care about studying graphs, after which we'll formally define the graph and introduce important terminology used to communicate ideas about graphs. Then we'll talk about how computers might represent graphs as a data structure, and then I'll finish the video off with some interesting problems and questions around graphs you can think about going forward. First, I'll proceed to formally define the graph. A graph is a set of vertices and edges where each edge is a connection between vertices. The way we usually denote an edge in a graph is by referring to it as a pair of vertices. And, as mentioned before, vertices and nodes are just different names of the same concept that we will use interchangeably when discussing graphs. Feel first to mathematically write down the definition of a graph in your set notation. For this particular graph, the vertex set looks like this, and our set of edges would be denoted with this notation. Let's now define some important terminology that you'll see over and over again when talking about graphs. The first important term is the concept of neighbors in a graph. Formally, two vertices are neighbors if an edge connects them. Here's an example. Vertices 1 and 8 of this graph are neighbors since they are connected by an edge. One thing that we will often query a graph for is all neighbors of a particular vertex. For example, if we were to ask for all neighbors on node 0, the result would be the following set of three nodes: node 4, 6, and 8. A related concept is the degree of a vertex. A degree of a specific vertex is equal to the number of edges connected to a vertex, or equivalently, the number of neighbors. As per this definition, the degree at vertex 0 would be 3. And the degree at vertex 3 would be 2. Let's now talk about paths. Paths are simply defined as a sequence of vertices connected by edges. Most of the paths that we deal with will be paths with unique vertices. For example, one path from vertex 0 to vertex 2 is shown here, and all vertices in the path only show up once, which is what we will assume most of the time. One feature of paths is that they have respective lengths. A path length is simply defined as the number of edges in a path. In this example, the path length we have here would be 4. A related idea to a path is the concept of a cycle. A cycle is defined as a path that starts and ends at the same vertex. One key note about cycles is that all cycles are paths, but not all paths are necessarily cycles. There are several cycles in this graph. Here's an example of a cycle that begins at vertex 0 and ends at vertex 0. The last term I want to talk about is the concept of connectivity, which can be used in several contexts. The first context is with respect to two specific vertices. Two vertices are connected if a path exists between them. The second context you may encounter connectivity is when it is applied to a general graph. A graph is connected when all vertices are pairwise connected. In other words, a path exists between all pairs of vertices. This graph is an example of a connected graph since, if you pick any two vertices in the graph, we can identify a path between them. However, if we change up the graph a little bit, we now have an example of a graph that is not connected. Now it's easy to see that no path exists between several pairs of vertices. This naturally leads to a third context that connectivity can be applied, which is the idea of a connected component. A connected component is a subset of vertices of the graph that is connected. For example, in this graph we have two connected components, the first being the following set of vertices, and then the remaining vertices of the graph form the second connected component. Let's now transition to the types of graphs that you may encounter. The main graph we've seen so far is specifically called an undirected graph. But for example, if I have an edge connecting vertex 0 to vertex 1, it's kind of implied that I also have an edge from vertex 1 to vertex 0. A graph where this would not be the case is called a directed graph, where no edges are unidirectional. Directed graphs also have their own classes. This particular graph has a cycle, so we can be more specific by referring to this graph as a directed cyclic graph. On the other hand, if a graph is directed and contains no cycles, we refer to that specifically as a directed acyclic graph, which is a specific subset of graphs that has been studied quite rigorously since they show up in all sorts of interesting bonds. Another important graph is a weighted graph. This graph is unique because each edge is now not treated equally, and some edges might have a larger weight than others. This can naturally model interesting metrics like traffic, distances on maps, and many other ideas. Another important class of graphs is trees. Trees have three key properties. All trees are connected in an acyclic. Moving an edge from a tree will disconnect the entire graph, and furthermore, adding any single edge to a tree will create a cycle. These are three loud examples of trees, and I encourage you to take a second, pause the video, and confirm that all these properties hold. Personally, I find verifying the second, third properties surprisingly satisfying. Really emphasize how fragile tree structure is, which I think is kinda cool. Let's now move on to some more hands-on ideas. How does a computer represent a graph as a data structure? Take for example the following graph. How would you go about organizing the information in this graph on a computer? Turns out that there are several separate ways to do this, and some of them are better than others depending on the context. The first idea that is quite natural is to map vertices to one another through a matrix, which we formally call an adjacency matrix. The rules for creating this matrix are fairly intuitive. If an edge between node I and j exists, we will indicate this with an entry 1 in our matrix. Otherwise, the entry will be 0. Following these rules, this is what our adjacency matrix looks like for this graph. Notice that each edge creates two entries since this is an undirected graph. Make sure you take a moment to understand the mapping we had here. The second dot representation of a graph is actually fairly simple. We take all the edges and construct a set with each edge as follows. This representation is called an edge set, and it also contains all the information about vertices and edges that you would need for a graph. However, this representation is not as common because it's a little harder to extract information about vertices of a graph using this particular representation. The third representation of a graph is called an adjacency list, and this is actually the most common representation used. The idea works as follows. We take each vertex and map the vertex to a list of its neighbors. For example, node 0 has 3 neighbors, specifically nodes 1, 2, and 3. So we map it to a list containing those values. The rest of the list is constructed in a similar manner. Nice thing about this representation is that it gives us an easy access to neighbors of a particular node, which is a tool that will be immensely useful in graph algorithms. Furthermore, this representation exploits the fact that most graphs in the real world are going to be sparse, meaning that we have a large number of vertices, with each vertex having relatively few edges. For example, in a social network, it would actually make the most sense to have this representation since there are going to be billions of nodes, but each node is unlikely to have more than a few thousand edges. An adjacency matrix for a graph like that would take way too much memory, but with an adjacency list, it's much more manageable. For this reason, in future videos, we'll primarily use adjacency lists as a way to represent graphs.